This is green. Your brain can easily say that it's green. But this also is a green. Even if the light detecting cells triggered in your brain are very different in each picture, your brain can easily tell that both are green. And if you want to build an algorithm to tell which is green, you can easily do that with basic mathematics. Let's look at this orange. It has an orange color, nice round shape, and if you touch it and smell it, it has a unique smell and feel. But if you look at the grapefruit, it has the same color and shape as orange. But when you see it and when you touch it, you know the difference between grapefruit and orange. Even if you don't know how do you recognize that it's a grapefruit, you can easily recognize that it's a grapefruit. But what if you want to write an algorithm that classifies grapefruits and orange in a big dataset? How could you code the algorithm even? Think how your brain knows the difference. Most of you knows what a neural network is, so I don't need to describe it again. As we all know, we don't need to know every little detail that differs orange and grapefruit. With help of neural networks, we can train a computer to recognize grapefruits. But what we need to build a neural network detecting grapefruits? Most of the neural networks require data that are tagged with human power, and they are using supervised learning steps. We can easily take a big dataset of grapefruits and orange with human eye. But what if we have a big amount of data that even we can't see the meaning? Like a multidimensional data from a complex experiment we had. For example, we experimented with potatoes and changed the lighting conditions, etc. And we need to classify this experiment data. We need something learned as a baby and unsupervised for this kind of needs. When you are a baby, no one tells you what is what, and you're just listening and seeing your surroundings and grouping every little thing you see. And by time, with these groupings, you result in a big knowledge database. So today we are talking about self-organizing maps. The most basic example of a self-organizing map is grouping colors. As we know, in computer, colors are represented with green, red, and blue dimensions. A color is a three-dimensional data in computer. And if we want to classify the color data in computer, we need to simplify it to 2 dimensions. Like this. This is a self-organized map generated with 3-dimensional color data into 2-dimensional color map. So what's a self-organized map even? Self-organized maps are unsupervised neural network type founded by Theo Koenen. It's basically a map of neurons with weight matrices to spec vectors of the data. For example, if we are dealing with an RGB data, it's a 3-dimensional data. We have a weight matrix from each neuron to spec vectors. So we have a weight from each neuron to each spec. So by doing that, we are organizing our self-organizing map. To do this, first we have to feed the self-organizing map a random weight vector. This is how it looks at the beginning when it's randomly arranged. After that, we are feeding the self-organizing map with our input vector. For this example, we have a blue color feed it into our map. When we feed a color into our self-organizing map, first our algorithm searches for the best matching unit. It calculates the distance from our input vector to each individual neuron, each individual dimension, and after doing that, is finding the best matching unit with the lowest distance to our input vector. After that, our algorithm determines neighborhood distance with an exponential function for each neuron in its neighborhood. Our algorithm slowly adjusts the weights of these neurons to the input vector, and for each step as our function is exponential, our neighborhood distance lowers, and it arranges the weights of the neurons, and by adjusting the weights of the neurons in the neighborhood of the best matching unit, we are grouping the input color in our self-organizing map. And as a result, we get from these random data to these organized colors. So we grouped our input colors and we reduced the 3-dimensional data to 2-dimensional data. So this is how self-organizing maps work. As I described the self-organizing maps, they are really helpful in data clustering, in data mining, especially when you are dealing with multidimensional data. But this process consumes a lot of computing power, and it costs a lot of time to process. To make this process faster, I implemented the algorithm in FPGA. So let's look at the implementation. Here you can see the top-down representation of the system. There are 3 different external devices connected to the system. One is serial device. It is responsible for controlling the system, as it sends the input vector and visualizes the output vector. The status LED shows the current status the system is in. For example, when the train is done, or everything is done, or best matching unit is found, one of the status LEDs are lit. The external noise generator is a noise generator made with tiny 85 microchips, and it is generating 6-bit random output. This 6-bit random output is important because every pseudo-random generator requires a noise source to make the pseudo-random process unpredictable. So, in our random process, we implemented 3 different linear feedback shift registers. And these linear feedback shift registers feeds itself with XORs, and with those XORs, it is generating a random output. But the problem here is, as long as the initial state of the linear feedback shift registers are known, we can know the output in any time. So the map generated with this linear feedback shift registers are always the same maps. So it's not actually a random map generator. So as I mentioned before, we use an external noise generator here, and at tiny 85. With this at tiny 85, we are generating an 6-bit random output. Let's look at the code here. So this is the code of the random bit generator implemented in at tiny 85. Here, with a set of functions, it is generating an 6-bit random output, and in each step, it is shifting the left linear feedback shift registers 6 right. So the 6 bits generated are exactly different each step. So here we can say a serial process, a controller, and K-map. The controller is the controlling entity of the system. It's managing the data flow between serial and K-map. It is controlling the system with a state machine. Here you can see the state machine's flow diagram, and this state machine has basically 5 different states, and each step is controlling whether the K-map is in train position or best matching in finding position or in waiting position. So let's look at the code how we done this step machine. Here is our controller entity. As you can see, there are inputs and some internal signals, and this is the process that reads the input from the serial. So this is basically looking at the serial. If there's an input in the serial which is not read and the input map is not done, so it's not read before, we are setting a flag to read the input read driver. And when the input read driver is active, then we look at this flag. This flag represents whether the first byte is read or not, because the first byte is how many input vectors there are. So if this flag is not set, then we are reading the incoming byte as input count, and until we reach the maximum input count, we are waiting the incoming data from the serial controller, and when we read the last input vector, we set the input map down flag to 1. So then we can move on the BMU and train state machines. This state machine is the one I showed before. So it basically in waiting state, in the initial state, looking if the current iterations we are running is lower than the iteration count we have, and if the map is ready. If the map is ready and we didn't reach the end of the iterations, we are setting the train step to BMU VS WS, and we set chosen input to the next we are processing. So in BMU WS states and BMU S states, it's telling the K-map to find the BMU, and when the BMU is found, we go to train S step, and in train steps we are telling the K-map to train the given neurons, and we are incrementing the neurons till we scan all the map, and then when we reach the last neuron on the map, we increment the current iterations. So we move on with wait state, and this goes on until the maximum iteration count is reached. And after that, we set a flag that tells the system that train is done. And when the train is done, we are outputting the data. This is basically reading each neuron and outputting the neuron to the serial controller. So let's go back to diagram here. Here we have the K-map. The K-map is the entity. We have the real map, and we do all the mathematical calculation. So basically there are 3 digital signal processors in K-map, and these digital signal processors are pipeline. So here, if we look at the K-map's code, it has only one process. In this process, first it initializes the map with random values read from the random generator, and when the weights are set for each neuron, then we are waiting the control signals from controller, It has actually two steps. One is train step, and in this train step, it is training the current neuron with the input vector, and basically it has some steps is because of the pipelining process. In find BMU state, it is finding the BMU by scanning each individual neuron and calculating the distance between each neuron and the input vector. It's actually the longest process we have here, most time-consuming process, and so when everything is done and controller runs the output, we have this get out process, and this process is reading each neuron and passing the weight vector to the controller, and controller passes to serial controller, so on. So that's all the K-map is doing. Let's move back to the scheme we have here. And the last thing we didn't discuss is serial entity. So let's look at the serial code. It has two state machines. One is for receiving the data and one is for transmitting the data. And it has a first in first out logic. And when it's reading a data, to don't miss the input vectors, it's putting the incoming data to FIFO. So it's just reading a data and putting it in the FIFO, and when a device, an entity wants to read a data, it pops a data from the FIFO and puts it in the data receive signal. And data transmit is working the same way. An entity puts a data to transmit, and this gets this data and puts it in serial. So this is a generic serial, and here as a default it's set to 9600 baud rate, but it can be changed. Everything done here is generic code. It's also same for the K-map. Here you can see the generic attributes. You can change all of this and all the code will work the same. Same for controller. As we explained all the system, let's test the system.
So this is our FPGA system. As you can see, there's a tiny 85 connected to our system. This is the noise generator we talked about. And here is our FPGA. The code is loaded. To test the performance and output, we are going to use an C++ implementation of the same algorithm written by me. Here you can see some of the code. Basically, I built a library for it. We will test both the FPGA and C++ implementation for the same input vector. It has 100 inputs in it. Let's see it. Here you can see the input vector. It's in CSV. And let's reset the FPGA and test. Here, as you can see, this is the random bit generated LED, and this is the map ready LED. It says that the map is ready to train. And let's press the run button for our Python script, and let's see the calculation time. And when we press the run button, you saw that the LED here flashed for a little. That was the time it was training, and it is done training, and it's now transmitting the data through the serial port. And you can see that it says reading output. That means the training is done and it's reading the output. The timer stops when the first data is received through the serial port, and as you can see, the overall training time is 2.9 seconds. And let's look at the visualized data. So here we have two R scripts. One is printing the random map read from the FPGA, and the other is our generated map. Let's look at the random map first. You can see the random map here. It looks random, no problem. And now let's see what our FPGA did. And as you can see, it grouped all the 100 colors and it looks pretty accurate. Now let's try the same with our C++ implementation and see how long it takes. Sorry, there was a problem with it. Now let's test it. As you can see, it read the input file and now training the map. And let's wait until it finishes the training. I don't know if you can hear, but my computer's fans are now running a lot. Yeah, here you can see the overall completion time. It completes the process in 21 seconds, and as you can see, the FPGA's performance is much better than the CPU implementation of the same algorithm. Consider that both the FPGA and CPU is running in a single core. Yeah, you know, there's no core in FPGA, but I didn't do any threaded processes, and by implementing some threaded processes, we can increase the overall time much lower. And thank you for listening to me. See you.